So first we'll see about microwave resonators. So resonators are used in various applications. They are used in oscillators, amplifiers, wave meters, and filters. Resonator they are designed at a particular frequency. They resonate. They produce maximum response. So the resonator will store energy in electric field for a capacitor and magnetic field for an inductor. At resonance, these two will be same, and the circuit will become a pure resistive network. So total energy is therefore twice the electric field or twice the magnetic field at resonance. So what are the different parameters we have for a resonator? So one is resonant frequency FR, that is when you have maximum energy value 2W or 2WM. Then the quality factor 2 pi into maximum energy stored by average energy dissipated per cycle. So Q is equal to FR by delta F. FR is resonant frequency, delta F is going to be the bandwidth. So for resonators, the Q value should be very high, or I can say the bandwidth should be very, very small or narrow bandwidth. So next one is input impedance. It has to be matching to 50 ohms. So Q factor will relate to how effectively it can store the energy. In order to obtain a very high Q, you have to use only reactive elements to design your network. And we are going to operate in a very high frequency from 100 to 1000 megahertz. So typical values of Q can be up to 10,000 are achieved by using transmission line sections. At high frequency, you have skin effect happening, so very high Q is not possible. So the value of Q will reduce from the maximum value. And today microwave cavities resonators are constructed using metallic cavities, which behaves like an RLC circuit. So you know how an RLC circuit will behave at resonance. Inductive reactance and capacitive reactance will cancel, and you will have a resistive effect. And since you're going to use metallic cavities, you will have loss that you can accommodate for the resistance R. And bandwidth is inversely proportional to quality factor.